In this example, we'll find the general solution on the interval from -π/2 to π/2 to the differential equation y double prime plus y equals tangent of t, and we will use the method of the variation of parameters. So our first step here, step A, is to find y1 and y2, the solutions to the corresponding homogeneous equation. So for this, we need to set up the auxiliary equation. The auxiliary equation for this differential equation is given by r squared plus 1 equals 0. And from this, it follows that r squared equals -1. And so r equals plus or minus I. Now let's write that down in terms of the general complex solutions, alpha plus or minus beta I. We see that alpha equals 0 and beta equals 1. So our general solutions look as follows. y1 of t equals e to the power alpha t cosine beta t plus e to the power alpha t times sine of beta t, or sorry, y1 is just, I was going to write down the general solution, but I still want to break this down into just y1 and y2. So I give the other one another name. So y2 of t equals e to the power alpha t sine of beta t. And so the conclusion then is when I plug in alpha as 0, this becomes a 1. And when I plug in beta equals 1, this just becomes cosine of t, and this becomes sine of t. So for part A, I find that y1 of t is cosine of t, and y2 of t is equal to sine of t. Okay, the next step is I want to find the Wronskian of y1 and y2. Now, the Wronskian is given by y1 times y2 prime minus y1 prime times y2. Now, we have y1 here, so we can quickly find y1 prime, and that is equal to negative sine of t, and y2 prime is equal to cosine of t. So let's write this out. So we have y1, which is cosine of t, times y2 prime, that's cosine of t, and then minus y1 prime is negative sine of t, and then y2 is sine of t, and that is cosine squared t plus sine squared of t. And that's the fundamental identity for trigonometry. And so what we find here is that the Wronskian of y1 and y2 is equal to 1. That's a good thing that will simplify our work going forward. So now we're at step 3. In step 3, we want to find v1 and v2. So let's write down the formula that we have for v1. That's the antiderivative of negative f times y2 over a times the Wronskian of y1 and y2 dt. Okay, so f is our function here on the right hand side. So this function here, tangent of t, that's our f of t. So our integral is negative tangent of t times y2, which we found to be sine of t, and then over a, which is the leading coefficient here. So we see that a equals 1. And so we're dividing by 1 times 1. The Wronskian we found to be 1. And then we can use the fact that tangent of t equals sine of t over cosine of t, and our integral now becomes sine of t squared over cosine of t dt. And what I use there is that tangent of t equals sine of t over cosine of t. Now to solve this, we want to write everything in terms of cosine. And so we can write this as minus, and in the sine squared we can write as 1 minus cosine squared t over cosine of t. And we will simplify that as follows, as negative, and then 1 over cosine t, that is secant of t. So that's the 1 over cosine of t, and then cosine squared over cosine, that gives us cosine of t dt. And we can then distribute that minus sign to make life a little bit easier and just write it as cosine of t minus secant of t dt. Now the antiderivative of cosine is sine, so that one is pretty straightforward. The other one, the antiderivative of secant of t, is not as straightforward, and what you will have to do there is probably look that up in a table of integrals, and what you find there is ln of the secant of t plus the tangent of t. And what I will do is on the midterm, I will actually provide you with a list of integrals on and I will post that on D2L as well. So this is our V1. Now we can choose any value for C. So what we'll do here is we'll just choose C to be 0. Choose C to be 0. And so the conclusion here is that V1 of t is equal to sine of t minus the natural log of secant of t plus tangent of t. And now we can find V2. So V2 we can find by integrating f times y1 over a times the Wronskian of y1 and y2. And we saw previously that f is tangent of t and y1 is cosine of t. And then we divide that by a, which is 1 times the Wronskian, which is 1. And fortunately for us, that simplifies a lot. If we use tangent of t as sine of t over cosine of t, we see that the cosine of t cancels out. And so this is just the antiderivative of sine of t. And that is equal to negative cosine of t plus constant of integration. Now, again, we're going to let that be equal to 0. And so our conclusion is that V2 of t is negative cosine of t. Okay, the fourth step for finding the particular solution is to find out that yp is equal to v1 y1 plus v2 y2. So in our case, we have that yp is v1, and v1 is this right here. So let's put that in between parentheses. That's sine of t minus ln of the secant of t plus the tangent of t and then we have that y1 is cosine of t, so we'll write cosine of t here, and then plus v2 is actually a minus cosine, so I'll replace this by a minus. So that is then minus cosine of t times y2, and y2, scroll up a little bit, y2 is sine of t, so that's minus cosine t times sine of t. Now, the final step is we have to find the general solution. So the general solution now is given by y of t is the solution to the homogeneous differential equation plus the particular solution, and the homogeneous equation, the solution to that is, and let's put this on the next line. So the homogeneous part is C1 cosine of t plus C2 times sine of t. That's the homogeneous part. And then our particular solution is sine of t minus ln of the secant of t plus the tangent of t, absolute value, times cosine of t, and then minus cosine of t times sine of t. And that is our most general solution. Now, what we have to note when we look at this differential equation, one thing to note is that this differential equation cannot be solved by the method of undetermined coefficients, because this right-hand side is not of the form e to the power rt, or a polynomial of t, or some kind of linear combination of cosine and sine. So this really is the only way to solve that with the methods that we have seen so far. Okay, now here's another example that builds on the previous example. So see that a particular solution is asked for the differential equation y double prime plus y equals tangent of t. So we only have to find a particular solution. So one thing that we note here is that this part right here, that is exactly example 1. And we've seen that the particular solution to that differential equation was given by this right here. So we know that if we're going to write a particular solution here, then we already know that that is going to consist by the superposition principle of two particular solutions, yp1 and yp2. And yp1, we just have to look at example 1. And we already have the answer there. And so for yp2, we have to look at this part of the differential equation. And that is something that can be solved by using the method of undetermined coefficients. So what we need to do is we need to compare t squared plus 2t plus 5. We're going to compare that with the general form on the right-hand side. Remember, that is a polynomial in t times e to the power rt. Now, when we compare this, we can think of this as t squared plus 2t plus 5 times e to the power 0t. And so what we see is that r equals 0, and that Pm of t, the polynomial, is t squared plus 2t plus 5. That's a polynomial of degree 2. And so that means that m equals 2. So for our particular solution, the second part, yp2 of t, that is a general polynomial of degree 2, a2 t squared plus a1t plus a naught times e to the power 0t, because r is 0. And then we have to worry about an extra factor of t. And that means we have to look at r equals 0 and compare it to the auxiliary equation and see if it's a root. Now, the auxiliary equation we found in part A, that's r squared plus 1 equals 0, and the roots of that auxiliary equation are plus or minus I. And so r is 0 is not a root of the auxiliary equation here. So we have t to the power 0. And so our particular solution actually simplifies to a2 t squared plus a1t plus a naught. So then yp2 prime of t is equal to 2a2t plus a1, and yp2 double prime of t is going to be equal to 2a2. Now let's plug that into this differential equation and set it equal to this part, right? So we want to make yp2 double prime plus yp2, that has to equal t squared plus 2t plus 5, and yp2 double prime, that's 2a2, and then plus yp2, that is a2t squared plus a1t plus a naught, and that equals t squared plus 2t plus 5. Now let's make the right hand side equal to 0. So we're going to subtract t squared from both sides. And what we get then is that we have a2 minus 1 times t squared, and then let's subtract 2t from both sides. So we're subtracting 2t here and 2t here, and then what we get is plus a1 minus 2 times t, and then finally we want to subtract 5 from both sides, and we see that the constant term here will become 2a 2 plus a naught and then minus 5. And then that is identically equal to 0. So what that means is, since this has to hold for all t, it means that a2 minus 1 equals 0. And so a2 equals 1. It also means that a1 minus 2 equals 0. So a1 minus 2 equals 0. So it follows that a1 equals 2. And then finally 2a2 plus a naught minus 5 equals 0. Plug in a2 equals 1, so we have 2 minus 5 is minus 3. So in the end, we get that a naught equals 3. And the conclusion here is that yp of t is yp1 from example 1 plus yp2, which is equal to a2t squared. a2 is 1, so that's plus t squared, plus a1t, so that's plus 2t, and then plus a naught is plus 3. And for completeness sake, let's just write this one out. So we have yp of t in total equals and let's look it up, sine of t minus ln of secant t plus tangent t times cosine t. Okay, so sine of t minus ln of secant t plus tangent of t, absolute value, all times cosine of t, minus cosine of t times sine of t, and then plus t squared plus 2t plus 3. And that is our particular solution for that differential equation.